Hello everyone. So today we are going to have some questions that came in your 22nd shift 1. My name is Anjali Yadav and the chemistry faculty. Let us begin. So let's look at the first question that came in your exam. The first question was, I think, pretty simple a question. It wasn't as such difficult. Let's see over here as compared with chlorocyclohexane. So let us write down the structure of cyclochlorohexane. Let us write down structure of cyclochlorohexane. Okay, so as you can see over here, there is not going to be any double bond or a triple bond that is present within the cyclic ring. This is cyclohexane. Which of the following statement correctly applies to chlorobenzene? So please remember, they are asking regarding the statements that apply to chlorobenzene over here, right? So let's see, the first statement that is given, the magnitude of negative charge is more on the chlorine atom, right? Is it? In chlorobenzene, the magnitude of negative charge. So first, let's look at here. Because of the resonance, what is happening here? Chlorine is a pretty electron withdrawing group, right? Is the electronegative group. So what will happen? There is going to be a partial double bond characteristics that is going to be formed over here, because the lone pairs on the chlorine atoms are going to participate in the benzene ring, because of which we are going to develop a partial double bond characteristic. So because of it, what will happen? The negative charge on the chlorine atom is not going to be more. In fact, it is going to be less. So the first statement itself is not correct. Okay, let's look at the next statement. The carbon-chlorine bond has partial double bond character. Absolutely right, like I've said. Next is carbon-chlorine bond is less polar, which is also correct. Yes, it is less polar. Next is carbon-chlorine bond is longer due to repulsion between the delocalized electrons of aromatic ring and lone pair of electrons on the chlorine atom. Again, there is a problem with this because it completely negates what we have said about here about the partial double bond characteristic. So that is not correct. Next is option E. The carbon-chlorine bond is formed using sp2 hybridized orbital of carbon. sp2 hybridized orbital of the carbon atom, which is absolutely correct, not a problem. This is carbon atom is actually sp2 hybridized. Okay. So correct option over here is going to be 3. Let's look at the next question, question number 52, which is a statement kind of a question that has been given to us. The first statement says that the benzene is nitrated to give nitrobenzene, which on further treatment with CH3COCl and AlCl3, can you identify this reagent? This reagent is for Federal-Kraft alkylation. Sorry, Federal-Kraft acylation. Okay, this is Federal-Kraft acylation. And if you look at Federal-Kraft acylation, what exactly happens over here? Your alkyl group, which is going to have a delta positive charge on it, has to be attacked by the benzene ring. Now, if you think about it, we already have formed over here nitrobenzene, right? If we have formed nitrobenzene, what does nitro does over here on the benzene ring? It is going to deactivate your benzene ring towards an electrophile. And that is why this reaction cannot actually happen. So the first statement itself is not correct. Let's look at the next statement. The next statement is nitro compound is meta-directing and deactivating group, which is correct, right? It is meta-directing and it is also deactivating, like I've just said. So this is an absolutely fine statement. So first is incorrect and the second is correct. So correct answer is going to be 2. Okay. Let's look at the next question. The next question is again statement, lot of statement type questions we have. Statement 1 is the Henry's law constant is constant with respect to variation in solution concentration over the range for which the solution is ideally diluted. Again, absolutely right. If you look at Henry's law, yes, it is going to depend on that. Henry's constant does not differ for the same solute in different solvents. See, Henry's law, if you look at the KH value, it is going to depend on the solvent itself, right? So if you change the solvent, the value of KH is also going to change. And that is why this next statement is wrong. So 1 is true and 2 is false. Okay. Let's look at the next one. In the reaction that is given to you over here, right? This is a well-balanced equation that is provided to us and they are asking the different options over here. Okay. So let's see. So first thing first, It is given over here. I'm going to do the first one and after that I'm going to do the last one so that you can see how we are going to get the correct answer, right? So first one is 67.2 liters of H2 at STP is produced for every mole of Al that reacts, right? So first of all, let us look at it over here. For every mole of aluminium that reacts, first of all, let's look at the ratios that they are combining with, which is going to be told by the coefficient that is present. So it is 2, it is 6, it is 2, it is 6, and it is 3 over here. Now they are asking between H2 and aluminium over here, aluminium and H2. So the ratio somewhere comes between 3:2, right? 2:3 ratio with aluminium and H2. So there they should be combining with in that particular ratio itself. So if we are providing for 1 mole, right? 1 mole meaning for 1 mole of H2 we are going to have 22.4 liters, right? Let me write it down over here when we are talking about STP, right? All right. So that means for 3 moles of H, every 1 mole. So if you have for 2 moles of aluminium, you have 3 moles of H2. So that means for 1 mole of aluminium, you are going to have 3/2 moles of H2, right? So similarly, for 1 mole of aluminium, you are also going to have 3/2 of H2. That means 3/2 of 22.4 liters, right? 22.4 liters. 3/2. And if you calculate this number, so this number I think should come out around 33.6 liters and not exactly 67.2 liters. So that means the first statement is not correct. So you have to see the combining of the ratios over here. Let's look at the option that is correct. The correct option over here is going to be the fourth one. Why the fourth option is correct is 11.2 liters of H2 at STP is produced for every mole of HCl that is consumed, right? So that means here we are looking at the reaction, the ratios between HCl as well as H2. So that means if you look at the ratio 6:3, or I can write it as 2:1 also if I want to simplify it even further. So after simplifying it, if you look at it, so yes, it is going to be half, right? If HCl is present, if I have 2 moles of HCl, half of it is going to be H2. So for every mole of HCl, 11.2 liters of H2 is going to be required. So that is absolutely correct. Okay. So let me write it down over here for those of you not to confuse anyone over here. So 2 moles HCl is going to combine with 1 mole of H2, right? And 1 mole of H2, and if we have been given every mole of HCl, so that means 1 mole of HCl is then going to combine with half a mole of H2, right? And 1 mole of H2 at STP is 22.4 liters, then half mole of H2 is going to be 11.2 liters. Yes, completely makes sense very nicely, no problem at all, right? Let's look at the next one, question number 55. Question number 55 says that the halogen that makes the longest bond with hydrogen and HX has the smallest covalent radius in its group. Now, if you look at the halogens and if you want to look at the bond length, the halogen that is going to make the longest bond length is definitely going to be iodine, right? So I know we are talking about iodine over here and has the smallest covalent radius in its group. Is it true? Not really. It does not have the smallest covalent radius. Absolutely not right. So if we are talking about iodine, who can make the longest bond with the hydrogen, definitely does not have the smallest covalent radius in the group. First statement is wrong. A group 15 element hydride EH3 has the lowest boiling point among the corresponding hydrides of other group 15. The maximum covalency of that element is. Now when we are combining, when we are looking at the hydrides of group 15 elements, this is how it looks like, right? We have pH3, which is going to be at the highest, then arsenic, then ammonia, and after that we have antimony. So highest is going to be pH3. Since it is pH3, that means we are being given pH3 over here. And when you look at the covalency, maximum covalency of phosphorus, nitrogen is definitely going to have a covalency, maximum covalency could be 3-4, right? But for phosphorus, not really. Phosphorus does have a d orbital present with it, so its maximum covalency is not 4, it is 6. So that means both our statements are wrong over here. Okay. Let's look at question number 56. A really good question, right? And let's see, a neutral organic compound is given to us, which is one of these. On treatment with aqueous Br2OH minus, A forms a compound B, which is soluble in dilute acid. B on treatment with aqueous sodium nitrate and HCl, that means you are making a disonium salt, as you can see over here, produces a compound C, which on treatment with CuC and NaCN will produce D. Hydrolysis of D produces E, which is also obtained from the hydrolysis of A. E on treatment with acidified KMnO4 produces F. F contain two different type of hydrogen atom. The structure of A is, so let us see what is going to be the structure over here for A, right? Let us start. So here, first thing first, the correct answer is going to be A itself. And let me walk you through the kind of a reaction that is going to happen over here. So let me make nice structures first. We have CH3, right? CONH2. Okay. The first reaction that they have given over here is that the compound on treatment with Br2 and OH minus, right? When it is going to react with Br2 and OH minus, then that means your CONH2, it's already soluble in dilute acid. On treatment next, it is going to be treated with sodium nitrate, right? So what are we making over here? We are going to be making amine. So here with Br2 and OH minus, we are going to have formation of just amine. Okay, amide is going to be converted to amine. Now amine is getting treated with NaNO2. As you guys already know, this is disonium salt formation. So we are going to have a disonium salt formation. Nothing is going to happen with CH3 as such, right? Till now, we are going to see what will happen next. So N2 plus and Cl minus is going to be formed over here. After that, they say that it's going to react with CuCN and NaCN, right? CuCN or NaCN. So as you know, our disonium salt is actually quite versatile when it comes to reaction, right? So it is going to make a cyanide over here. After that formation of a cyanide, we are going to have reaction with, what else do we have? Hydrolysis. We have hydrolysis of it. So let me write down here as H3O plus. And when we are going to do hydrolysis of it, CN is going to be oxidized to your carboxylic acid, right? So let us write that down over here. We are going to have CH3 group. We are going to have carboxylic acid over here. Now coming to the next part, last part, which is acidified KMnO4. This is KMnO4. So when it is going to react with KMnO4, KMnO4 is a really good strong oxidizing agent. So it is going to oxidize our CH3 group over here to an acid. So we will have COOH and we will also have here COH. Okay, as you can see, this is how the reaction is going to go. Option A over here is going to be considered to be correct. And if you want me to mark it down a little bit, what is A and all that, so this is your A, this is I think B, C, D, E, and this is F. Okay, I hope it is crystal clear. Terribly sorry about the handwriting, but I hope while I was writing and while I was speaking, you got the idea of what is happening over here. Little bit of less space. I think I should have taken one extra page. Let's see. Let's look at the next question. Two p-block elements X and Y form fluorides of type EF. The fluoride compound XF3 is a Lewis acid and YF3 is a Lewis base. The hybridization of the central atom of XF3 and YF3 is. Now, if you think about it properly, two p-block elements are there and we have a Lewis acid as well as we have a Lewis base. Lewis acid meaning those compounds which are electron deficient, right? Either positively charged or electron deficient. That means over here XF3 is electron deficient. If it is electron deficient, that means definitely it must be element that is coming from group 13. Okay, and if we look at YF3, which is a Lewis base, that means it has unpaired electrons, lone pair of electrons that might be present on it, or a negative charge. In this case, it is going to be lone pair of electrons, right? So that means it must be present from group 15, right? So according to us, if it is present from 3A group, could be, for example, right, it could be BF3, and we have talked about a lot in our classes also, BF3, electron deficient compound, aluminium, AlCl3, also electron deficient compound, right? All of them which belongs to the third group itself. Coming to the 5th A element, that means here we have ammonia. Let's take ammonia, right? Does have a lone pair of electron on it, right? Now let's look at the hybridization that we are talking about, since it is going to be a planar compound, right? This is trigonal planar. Trigonal planar, it is going to be sp2 hybridized. If you remember, your ammonia is actually pyramidal in shape, right? Pyramidal with a lone pair of electrons, so that means this is going to be sp3 hybridized. Okay, so we have sp2 and sp3 hybridized, that means option 1 is going to be correct, right? Let's look at the next question, question number 58. Really easy question, really good question. I personally feel it's quite easy to solve, match the following, because anyway you get a hint of your answer, and if you're really lucky, if you solve 2 or 1, you will get the answer on your own. So you don't have to know completely everything about it. It's really good if you do. I would encourage it. But if you don't, still you have a chance in a match the following type of a question. So according to me, I think the easiest one that I can actually find to look at it is Wolff-Krishna reduction, right? Wolff-Krishna reduction over here, third one, right? And after that, the next silver is present. As soon as you see silver, you definitely know that it must be the tolerance test, right? Then after that, we have copper sulfate, sodium potassium titrate, and KOH, which is nicely a Fehling solution that has been given to us. And the last one is ZnHg and HCl, which is going to be Clemmensen reduction. Okay, right? So both Fehling test and tolerance test is done test for your aldehydes itself, if you guys remember, right? And after that, your Clemmensen is for acidic reduction. All right. What the correct answer here is going to be 3. Let's look at question number 59. Question number 59, the correct order of rate of reaction for the following reactants with nucleophile by SN1 mechanism. As soon as you see SN1 mechanism, you have to think about carbocation. How you can form a stable carbocation, only that, because the first step is the rate determining step. The first step is formation of carbocation. That means carbocation formation is what you have to get priority to. So according to that, if you see over here, if you remove the halogens from here, the positive charge is going to be at these places. So what do you have to give priority to? You have to give priority to cyclic benzylic. Okay, first benzylic, because then there is going to be a part of a resonance. So that would be great. So benzylic, then tertiary, then secondary, and then primary. So first of all, there is a good competition between first and the second one. After that, you also have to check regarding the stability. You have to check regarding the resonance, right? So really not going to be as such, because they are not going to be planar in that way, right? So here the correct way is going to be the fourth is going to be the correct one. After that, we are going to have the third, right, which is again going to be the tertiary carbon atom that is present. This is going to be very nicely stabilized by the resonance that are present around it, right? Phenyl group, and phenyl group that are present. So if you get a positive charge over here, nicely stabilized by the resonance that is around it, right? Next is going to be third one, which is tertiary carbocation that is going to be formed over here. And after that, the next one is going to be the first one, right? And the last one will be the second. Okay, so correct answer here is third. Let's look at question number 60. Question number 60 is statement kind of a question. Statement says that phenol on treatment with CHCl3 aqueous KOH under refluxing condition followed by acidification produced para-hydroxybenzaldehyde as a minor product and ortho-hydroxybenzaldehyde as a major product. Now, if you think about it, usually para-hydroxy are the ones that are usually going to be, we would say, more major product most of the time. So let us just make the structures over here. They are saying benzaldehyde, ortho and para, right? CHO. So this is your ortho compound. Now, if you look at the ortho compound over here, why it is going to be the major product is because of very nice hydrogen bonding that can happen, right? And because of hydrogen bonding, ortho is going to be the major product, para is going to be the minor product. Apart from that, statement 2 is the mixture of para-hydroxybenzaldehyde and ortho-hydroxybenzaldehyde can easily separate it through steam distillation, which is again true because in ortho-hydroxybenzaldehyde there is intramolecular hydrogen bonding, whereas in para-hydroxy it is going to be intermolecular hydrogen bonding. When we talk about boiling point, it is the energy is first going to be required to break the bond that is within the molecules. So if within the molecules, that means intermolecular bonds are going to be harder to break, more energy, more temperature is going to be required, more is going to be the boiling point, right? So para will have more boiling point, ortho will have less boiling point, and so we can easily use here the second option, which is steam distillation, which is based on the difference in boiling point. So this statement is absolutely correct. Both the statements are absolutely fine. So correct answer is 4. Let's look at the next question, question number 61. Question number 61 is with respect to the very simple formula, which is of a formal charge. So let us write down the formula for a formal charge first. First, you are going to write down the valency. After that, you are going to write down the lone pairs that are present. After that, you are going to write down the bond pairs, right, divided by 2. So this is the formula that we are going to be using for the formal charge. So let us start with it one by one. Okay, let's see what all do we have, right? So let's see for the first one, for the first oxygen atom that is present, let me write down over here as 1. Add oxygen, so this is going to be 6. How many lone pairs that are present over here around it? The number of lone pairs that are present is 4. The number of bond pairs that are present is 4 by 2. So this is going to be 4 minus 2. Oh, sorry, plus. Absolutely. So this is going to be 4 plus 2. So this is going to be 0. So there is no formal charge in the first one. So we have 0 in all the options. Let's go to the second one. Second one is nitrogen. So nitrogen is going to have a valency of 5. How many lone pairs do we have? We have 0 lone pairs. How many bond pairs do we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2. And here it is going to be 4. So this will be plus 1. So next one should be plus 1. So I think we have already found our answer. The answer is going to be 3. But let's go through all of them, right? So let's talk about the third oxygen that is present over here. It is going to be 6 minus how many lone pair? 4. How many bond pair? 4 divided by 2. Again, this will come out to be 0. Let's look at the fourth one that is present. 6 minus 6 lone pairs are there and 2 bond pairs are there, right? And this will give you the number. So we have 1, 7, negative 1. Okay. So as you can see, exactly matching the pattern very nicely without any problem. So you have to know the formula for the formal charge. Let's look at the next question, question number 62. Question number 62 is the energy required by the electron present in the first Bohr orbit of hydrogen atom to be excited to the second Bohr orbit is how much? RH value is already provided to you. So whenever we are given from the first excited level to the second excited level and so on, right? So what do we have to do in such a condition? We have to write down the formula for the change in energy, right? And this is the formula that we have, okay? So when we have this formula, so we have to put down here the values of E1 and E2 very nicely, right? And when we do that, RH value, right? So now everything is already present over here. All we need to know was the formula. So we have 2.18 into 10 raised to the power of minus 18. Over here, this is going to become 3 by 4. And here it is going to be 6 into 10 raised to the power of 23. Because they are talking about an electron, required by an electron. So we have to multiply it by Avogadro's number as well over here. And when you solve this question, you will get the answer as 9.8 35 into 10 raised to the power of 5, which is your option 1. Okay. Let's look at the next question, question number 63. Question number 63 is a pretty simple question. They were just trying to trick the students a little bit. Let's see over here. The first thing is it's a first order reaction. As soon as you see the first order reaction, you know the rate is going to depend only on the concentration of reactant. So if I make the concentration as same, then that means what will happen for the same kind of a concentration, we are going to have same kind of a rate. Okay, same concentration, same rate. And if you see over here, what they have done is, in the first one, 100 ml in 10 molar solution of reactant A. So as long as they are able to make a 10 molar solution, that means concentration is same. For the first and the second one, in both of them, 10 molar has been taken up, right? Which is fine. Now, what they have done is, in the third one, they have diluted it further by adding 100 ml of water. So now the concentration, after having this kind of a solution, if you add more water, definitely the concentration is going to change over here, right? It has become more diluted. And because it has become more diluted, that means the correct answer over here is going to be the second one. Third is going to be the last. Right, the rate is going to be less, and the first and the second one is going to be same, because as long as the concentration is same, the rate is going to be same for a first order reaction. Let's look at the next question. Next question is, the first raw transition metal does not liberate H2 gas from dilute HCl. 1 mole of aqueous solution of MSO4 is treated with excess of aqueous KCN, and then H2S is passed through the solution. The amount of MS, that means metal sulfide, formed from the above reaction is how many moles? So of course we have to look at the reactions over here. So first row transition metal does not liberate H2 from dilute HCl. 1 mole of aqueous solution is treated with. So first row of transition metal that does not liberate H2 from HCl is your copper. Right? So we have identified this is the copper sulfate that they are talking about. Let us look at the reactions. Copper sulfate plus KCN is going to give you this compound. Now, if you can see over here, K3CuSO4, copper sulfate, right? Potassium copper sulfate. So here, as you can see, if it is react with H2S, there is not going to be any PPT. The reason for having no PPT is there is no copper group that is present or any other group that is present outside the coordination sphere to actually react with it to actually make up a PPT. Okay, and because it is not present outside, so that means it is going to be 0, right? No metal sulfide as such is going to be formed over here. Next is, consider the transition metals that are present and form low spin octahedral complexes. The correct decreasing order of unpaired electrons in their respective d orbital of the complex is which of the following? So first thing first is definitely going to be writing down the electronic configuration for each one of them. So if it is manganese plus 3, if you remember, it is going to be 3d5 4s2, right? 3 electrons I have to remove, so we are going to be left with 3d4, right? Similarly for chromium, it is going to be 3d3. For iron, it is going to be 3d5. For cobalt plus 3, it is going to be 3d6. They are saying all form low spin octahedral complexes. What do you mean by low spin octahedral complexes? That means we are talking about strong field ligands over here, right? The correct order of unpaired electrons. So let's try to find out the unpaired electrons now if it is going to be strong field ligand, right? So how are we going to fill the electrons over here? If it is a strong field ligand, then that means T2G and EG, can I write in this way? I think it is going to be much more easier for us. Okay, so if it is D4 over here, that means all the 4 are going to go. It's a strong field ligand, so pairing is going to definitely take place over here. So this is going to have how many unpaired electrons then, right? If it is, we write it down as 3, so it will be 1, 2, 3 and 4. So there are going to be 2 unpaired electrons that are present. Okay. Let's look at the next one. We have how many unpaired electrons? We have 2 unpaired electrons over here. Then after that, we have 3d3 electrons are only present. So all are going to go in T2G. It will be 3. After that, we are going to have D5. If you have D5, So all 5 of them are already going to be in T2G itself. So if you write down T2G, right over here, 1, 2, 3, 4, 5. 1 unpaired electron is present. So this is going to be 1. After that, the next one is going to be cobalt over here. Cobalt with D6. All the 6 1 are going to be present over here itself in the T2G. All of them are nicely paired up. So this is going to be 0. Okay. So that means over here, what do we have? The highest is chromium. After chromium, we have manganese. After manganese, we have iron. And then we have cobalt. So correct answer is going to be 4. Right? Okay. Let's look at the next question. The next question is the correct order of reactivity of CH3Br and methanol with the following nucleophile if F minus I minus C2H5O minus and C6H5O minus. Now, if you look at over here, we have been given a nice benzene ring, and this is ethane compound, fluorine and fluorine and iodine are also given. When we look at the reactivity, we have to look at the ability of a good leaving group also, right? So of course, the best kind of a leaving group we definitely have is iodine. The worst kind is going to be your fluorine, right? So that means the first should be iodine, the last should be fluorine. Definitely the correct answer is going to be 2. Apart from that, the next one between C2H5 and C6H5O minus, C2H5O minus is going to be a better candidate, right? As compared to C6H5O minus, right? And the worst is of course fluorine as a leaving group. Let's look at question number 67. The p block element and the hydrogen forms a binary cation, okay, which is EHX plus, while EH3 on treatment with K2HGI4. As soon as we see K2HGI4, what is this? This is Nessler reagent, right? And because I've identified Nessler reagent, that means we are definitely talking about nitrogen ammonia over here, right? Now that I know that this is nitrogen that we are talking about, what they are exactly asking is the value in kilojoule per mole for the first element, that means first ionization energy, for the group 13, 14, 15 and 16. Between, if you already remember, 15 is the group that is going to have the highest first ionization energy, because you are going to be taking out the electron from the half-filled orbital, which definitely requires more energy as compared to its neighbors, right? And as you can see, 15 is also coincidentally our own element that we were talking about, which is nitrogen. So I have to find out the highest number among all the following. Highest number is 1402. Okay, so correct answer is 1402. If you want to look at the reaction with respect to the Nessler reagent, so this is Nessler reagent. When it is going to react with ammonia in the presence of potassium hydroxide, we are going to get amido, iodo, mercury, potassium iodide and water. Okay, reaction as such not asked to you, but of course if you want to know something extra, this is here, right? Precipitate of basic mercury amido iodine is very nicely formed by us ammonia. Okay, with Nessler reagent. Let's look at the next question given below are 2 statements. Sucrose is dextrorotatory. However, sucrose upon hydrolysis gives a solution mixture of product, which as you guys already know is glucose and fructose. This solution shows levorotation, which is absolutely fine. The statement is correct. If you look at the numbers, if you look at the optical numbers, glucose is going to be plus, which is dextrorotatory, 52.7 degree. Fructose is negative 92 degree, right, which is levorotatory. So levorotatory is definitely more. So solution is going to show more levorotation. Next statement, hydrolysis of sugar give glucose and fructose. Yes, since the levorotation of glucose, that is not correct, right? Levorotation, no. Dextro. Dextrorotation of glucose is more than the levorotation of fructose. The resulting solution becomes levorotatory. Now it is fine. So that means the second statement, there was tiny bit of a problem. So this is wrong. And first statement is correct, second statement is false. So correct answer is going to be 2. Next question, question number 69. Now question number 69 is a pretty good question. It's a time-taking question, but definitely an easier one. If you remember the formula, it is not going to take you a lot of time, right? So we are going to go with each of the options one by one. So I've written it very beautifully in the next page itself, right? Let's see. Work done in a reversible isothermal expansion. As soon as you see reversible, you know we are going to be using the integrated formula for the work done over here, right? When we use the integrated formula for the work done, the formula is 2.303 RT log V2 by V1. Values are very nicely given. 2 moles of ideal gas, 2 decimeter cube, 20 decimeter cube at 300 Kelvin. We just have to put down the value. You will get the answer as 11.5. Okay. Next is the work done in irreversible. Very good. If it is irreversible, then it makes the job very easy. We have a very simple formula, P delta V, right? So we're going to use that formula over here. Moles are given, which is 1. Pressure is given to you. Temperature is given to you, which is not really required, and volume is given. So here we just have to put down the value. It's given in kilopascal. So we're going to convert into Pascal by multiplying it into 10 raised to the power of 3. 3 minus 1, and you will get the answer as 6 into 10 raised to the power of 3. Next is change in the internal energy for adiabatic expansion. As soon as you see adiabatic expansion, heat is constant. Okay, 1 mole of ideal gas with change in temperature. They're asking for internal energy. CV value is already given to you. And as you know, we do have a very simplistic formula, internal energy with respect to CV, which is NCV delta T. Okay, so let's put down the value over here. NCV dt. Temperature is given to us. C value is given to us. R value, you're going to take it as 8.314. Your answer is going to come in joules, which nearby should be 4 kilojoules. Okay. Next is change in enthalpy of constant pressure of 1 mole of ideal gas with change of temperature 337 Kelvin. Kp value again is already given to us. So of course, when we have internal energy, the formula is with respect to CV. When we have enthalpy, the formula is with respect to Cp. Let me just see if you are able to see the bottom of this. So NCP delta T, T value is already given. The change in temperature is already provided to us. R value 8.314 we are going to take. This is going to be 7,000, which is 7 kilojoule. So as you can see, the formulas are very simplistic. It's just given in a match the following, so you don't have to solve each one of them. You have to solve at least 2 or 3 of them and you will get your answer quite quickly. For the first one, it is 11.5. For the next one, I believe it was somewhere 6, right? Yes, 6 into 10 raised to the power of 3. So it is going to be next 6. Here it was 4 and here it was 7. The correct answer is going to be, okay. Let's quickly look at the next question. Consider a solution which is carbon dioxide dissolved in water in a closed container. Which of the following plot correctly represent the variation of log partial pressure of carbon dioxide in vapor phase above water, and then after that y-axis the log mole fraction of carbon dioxide in water, x-axis is given, and 25 degrees Celsius. So if you look at the formula, how we are going to write it down for this, it is going to be partial pressure KH and your mole fraction for carbon dioxide. If you take the log value for each one of them, as you can see, this is y is equal to mx plus c, right? It's definitely a formula for or equation for a straight line where your there is an intersection point and your slope is positive. So that means it should be upwards slope and there is an intersection, so you should not start from 0. The correct answer is going to be 2. Next is consider the following electrochemical cell at 298 Kelvin. So now we are starting with the integer type questions. There were 5 integer type questions. Equation is very nicely provided to us over here. If the reaction quotient of a given time is 10 raised to the power of 6, then the cell EMF is what? And 10 raised to the power of minus 1, you have to find out on the nearest integer. E0 value for both of them are very nicely provided to you for reduction as well as oxidation for cathode on anode, right? Whichever way you want to call it. So let's look at the first one over here. We have HSNO2 minus. If you look at the reaction over here, there are going to be 2 electrons that are released, right? So that means N value over here is going to be 2. Okay. Now we are just going to use the plain simple Nernst equation. For this, E0 value, as you can see, is going to be 1.34, right? Which is going to be E0 cathode minus E0 anode. Okay. Now what we are going to do is we are going to put it down in the equation over here. So let me write it down, 1.34 minus 0.059. If you want, you can also take it as 0.06. That is also fine for ease of your calculations. and log 10 raised to the power of, what was it? Reaction quotient 6. So that means it is going to come out to be 6 over here, right? So the correct answer, your answer is going to come nearly equal to 4. Nearly equal to. So 4 into 10 raised to the power of -1, of course. Okay. Let's look at the next question. Now this is a pretty good question. A little longer for sure. Dissociation of a gas A2 take place according to the following chemical reaction. At equilibrium, the total pressure is 1 bar at 300 Kelvin, A2 to 2A, right? The standard Gibbs energy for the formation of the involved substances has been provided over here. So delta G values are already presented to you for A2 as well as A. So as you can see over here, I can find out the delta G value. From delta G, I can find out the K value, right? Through the formula minus RT log K, natural log K. Okay, if you want to put log, 2.303 minus RT, 2.303 log K. From there, we can find out the value of K. To help with that, they have already given us the log value very nicely, which is really good, right? R value, they asked us to take it as 8 joules per mole per Kelvin, right? Assumed degree of dissociation is not negligible, right? So let us look at how we are going to solve this question. So first is, I'm going to find out the delta G of the reaction. So delta G of the reaction over here is going to be 100 minus 101.664, right? So this will give us minus 1.664 as the answer. 2.303, I'm going to put it in the equation for RT log K. Okay, from here we can find out the value of K, which is going to be 2, right? Coming to the next part over here, if we are going to write down the equation, what was the equation? A2 to 2A. Okay, let us start initial, let's say P, and this is 0, and after that let's say our equilibrium, it is going to be P 1 minus alpha, this is going to be 2P alpha. So alpha, okay. Now total moles will be P minus P alpha plus 2P alpha. This will give you P minus P alpha. P plus P alpha, that means I can write it as P1 plus alpha. Okay. So this is with respect to your total number of moles, right? After that, of course, if I want to find out the partial pressure for each one of them, I'm going to use the Raoult's law, where I'm going to use the number of moles divided by total number of moles into the total pressure. Okay, so let's write down for first A2. Okay, what is the number of moles for A2? P 1 plus alpha, right? Denominator, the total number of moles, which is P, sorry, this is 1 minus alpha. The next is going to be 1 plus alpha, right? And total pressure. This is how we can write down. Similarly, we can go for A as well. It's going to be 2P alpha. And here we are going to have, of course, you can cancel out all these things, not a problem. Then we have P 1 plus alpha. Again, cancelling out these parts of P. And P total is already there. Okay. P total is already given to us, which is 1. So, not a problem over there. Let us write down now the formula for Kp. Okay. Kp formula is going to be partial pressure of A raised to the power of 2 and partial pressure of A2. So, let's put in the value. Partial pressure of A is over here 2 alpha, 1 plus alpha and Pt raised to the power of 2. Then we have 1 minus alpha, 1 plus alpha and total pressure. Okay. So as you can see, we are definitely going to simplify the equation a little bit over here before we put down the values, right? So let us try to do that. So it is going to be 4 alpha square. This is going to be 1 plus alpha square. And here it is going to be 1 minus alpha, P total square. This is P total. So this is going to get cancelled out. 1 plus alpha. This and alpha square is going to get cancelled out. So we are going to be left with 4 alpha square Pt 1 minus alpha square. So 1 plus alpha, 1 minus alpha, I can get 1 minus alpha square from here. Now, so this thing is going to become as 1. So from here, what I'm going to do is I'm going to keep the value of Kp, which I found it to be 2, right? And what we are going to do over here is we are going to put down the value. So our answer has to be just a nearest integer, right? So this is the kind of a reaction that we are going to get. Now, if you solve the equation over here, alpha value is actually going to come out to be near to 33 into 10 raised to the power of minus 2 and raised to the power of half over here. Is it minus 2? Yes, raised to the power of half. When you're going to solve it for alpha values, you're going to get this value. And like I said, assumed degree of dissociation is not negligible, so we are not going to keep it negligible. We are going to keep it as it is and then solve the question. So here it is going to be 33. Let's look at the next question. The next question is 73. Cyclohexene on bromination consumes 1 mole of bromine per mole and gives the product in which carbon-bromine ratio is 3:1. The percentage of bromine is product Y is how much? So first of all, this is the reaction that how the reaction is going to look like. We have been given cyclohexene, that means 1 double bond. When it is going to react with Br2, both the double bonds are going to get the bromine atom, which qualifies for 3:1 rule. So 6 carbon, 2 bromine. So 3:1. The percentage of bromine in the product is going to be how much? For that, what do we need to find out? First of all, I need to find out the molecular mass for this whole compound. It is C6H10Br2. All the values for hydrogen, carbon, oxygen and bromine are already given to you over here. And it's going to be complete molar mass of, so this is molar mass. Okay, so let us find out the percentage of bromine. How will we do that? So first of all, the atomic mass of bromine, which is 80, which they have said us to take as 80, so it's 79.9 something. After that, the number of bromine atom, which is into 2, divided by the total mass, which is 241.90 into 100, since we are talking about percentages over here, and this value is going to come out to be near to be 66. Okay, since they have said us to calculate to the nearest integer, and the nearest integer is going to be 66. Okay, let's look at question number 74. Question number 74 is also a pretty easy question because they have already given us everything, right? They have told us that the temperature at which the rate constant of a given below 2 gaseous reaction become equal is. So first, that means we have to make them equal. We have to equate both of them together, right? And then look at the values that are provided. So when we are going to equate both of these together, as you can see over here, minus 30,000 by T, minus 24,000 by T. We are going to take it on the other side over here. We are going to get 6,000 by T, and this is 100, right? So you can take it on the other side. You are going to get 100 over here. And after that, if I want to remove the E value, as you can see over here, I will have to put a natural log to the other side. So it is going to be 2 natural log 10, okay? Because 100, natural log of 100 is 2 natural log 10, right? So you can write it as 10 raised to the power of 2. And I've taken 2 outside. I hope you are able to understand this. So I've just skipped a step over here and written it directly. Now, of course, if I want to remove the natural log, I have to multiply it by 2.303. From here, I want to find out the temperature. So it is going to be 6,000. 2 into 2.303. Temperature is going to be 1303 Kelvin. Okay. Let's look at the last question for today, right? So sodium fusion extract of a organic compound with CHCl3 and chlorine water gives a violet color to CHCl3 layer. 0.15 gram of Y gave 0.12 gram of silver halide precipitate in Carius method. Very good. So what do we have to do over here for a Carius method? That means we have to write down the formula, put in the values, get to the answer. Okay, percentage of halogen in the compound is going to be nearest to what? So first of all, if I want to find out the percentage of iodine that is present over here, which is Y, the organic compound, right? The organic compound value is given. So percentage of iodine for here, it is going to be atomic weight of iodine, mass, which is already given to us as 0.12 gram of silver halide, right? Okay, so mass of your AgI divided by the molecular mass of AgI, right? So this is molecular weight of AgI. This is your weight of organic compound. Mass of AgI, okay, already given to us. So molecular weight of AgI, we can easily calculate all the values represented, which is going to come out to be 235. And atomic weight of iodine is already given to us, which is 127. Mass of AgI is given 0.12. Weight of organic compound is also given to you as 0.15 into 100, and you will get 43.23%. Okay, so very basic formula. Whenever you get a formula for specifically Zelda-Dumas carriers, which is come every single year in every single paper, right, you have to memorize the formula really well. You should understand what is the concept behind it. Okay, that will give you a really good idea, right? So that's all for the paper, and I hope all the very best to all of you for if you are giving a JEE Main session 2, or if you are going for advanced. Many congratulations to you. Thank you so much. Have a great day.